Welcome to the E-Pathshala series in computer science. This is the 11th module in the subject of cloud computing. So, in the last class we saw how external and internal clocks can be used to keep our server times synchronized. We saw that since servers are geographically dispersed, we need to synchronize them so that various events are given the correct time and are done in a coordinated manner. We discussed Christian's algorithm for external synchronization, we discussed Berkeley's algorithm for internal synchronization, and we discussed about the how to set the clock. So, this class we will see how we can synchronize our clocks without the need of any external or internal clocks. So, when we say synchronize, we are trying to synchronize the clock values, but actually what we are synchronizing are the various events. If we look back at the example we have taken of Rina trying to attend her class or Ram and Nita trying to book the last ticket for IPL, we will see that the events that they are actually executing are the ones that were being synchronized, not actually the time. We really do not care much about how the clock runs if we have these events properly numbered. So, let us look at what is an event. An event is something that happens in a process. So, anything that occurs in a process is an event. So, running a consumer's processor application is an event. That means executing every instruction in that processor application is an event. Updating a database with the values is an event. A message sent by a process to another process to in the same machine or in a different machine, from one data center to another data center, from one geographic location to another geographic location are all events. Similarly, any execution of receiving process is also an event. A reply to the message received is an event. So, we define an event to be any occurrence in the process. So, let us look at an example where we have two databases. They are replicated databases which are copies of each other, and we have this database in Delhi and the other database in South Africa. The account balance in these two databases of a certain account is 1000 rupees. Now, in a replicated database, the requirement is that the databases should always be the same, identical. So, let us look at what happens. There is a user who is in New Delhi and we have another user who is in South Africa. User 1 in New Delhi is trying to add 5000 rupees to this account, and user 2 is trying to do the update of 10% interest to this account. Now, both are trying to do it at time T1. Now, T1 is in New Delhi server and T1 at South Africa server. These are the two T1s that we are talking about. So, we have the two databases, two users and two updates. Now, when the first user does update 1, it executes, it sends the result in DB1 and it also sends the result in DB2. Similarly, when update 2 happens, it is updated in DB2 as well as in DB1. So, what will happen in reality, although both the updates happened at the same time T1, and even if I have assumed that the clocks are synchronized, which means that they are actually T1 in or real time, what will happen is update 1 in DB1 will be arriving first and then update 2 will arrive, because the user is in the same geographic location as the database. Similarly, in South African server, what will happen is the DB2 will arrive first and then the DB1 will arrive. Now, is this a problem? Let us look at whether this actually is a problem or not. The balance of this account after the two updates will be different in the two databases. When we say that the databases are replicated, we automatically assume that the system will take care of synchronizing the values. Always the values in the two databases must be the same. But here in this example, we see that the two updates actually are causing the two databases to be not in sync. So, what will happen? This update 1 will come first and update 2 will come next in DB1, and the account balance will be 6,600, whereas update 2 will first arrive in South African database and then update 1 will arrive and the account balance will be 6,100. An inconsistency in the database which is not at all acceptable in the cloud based user. So, what is the way out of this? We have a solution in something called a timestamp. So, we instead of synchronizing the clocks, we order the events using the number, using some numbers rather than the absolute clock time. What is it that we are trying to do? We are assigning timestamps to these events. So, two questions that we have to answer is timestamp, how do I generate this timestamp, and what is the condition that has to be followed by the mechanism. Timestamp can be just the number. So, therefore, I can start with 0 and for every event we can increment the number by 1 or any number for that matter, and we call it a timestamp. So, timestamp is a very simple mechanism. Now, what is a condition that we need this timestamp to obey is that it should obey the condition of causality. So, let us look at what is causality. Causality is if some event A is after or before another event B, then the timestamp of A should be less than timestamp of B. So, if an event A has occurred before event B, then the timestamp of A should be less than the timestamp of B. As long as this is followed, we are happy with the timestamp. So, we use in real life causality all the time. We say that Rina entered the class before the teacher. So, we do not look at Rina's clock and teacher's clock to see or understand this event. What we do is we say there are two events, one Rina entering the class and two teacher starting the class, and these two events happened at a certain order, and if Rina has entered the class before the teacher started teaching, then her time is this event has happened before the teaching event. Similarly, when we receive a mail, the mail should have been sent before the receive event has occurred. So, as long as we can find a way of time stamping which obeys the causality, which is this happened before relationship, we call it a happened before relationship, we can use this. So, let us look at the precedence of events. An event precedence indicates which if an event has occurred when. All the precedence in one process will be known to each other. This is called the happened before relationship. This is indicated by this arrow, and when we say EI has happened before EJ, we mean that EI is an event which has occurred before the event EJ, irrespective of where EI has occurred and where EJ has occurred. So, the precedence of events in a process is known, and this cause and effect relationship is actually captured by the happened before. So, here is a time diagram example. As we said, P1 and P2 are two processes. Using the timing diagram example, E21 is an event happening in P2, E22 is the second event. So, how we frame this is EIJ, where I is the process ID and j is the jth event in the ith process. So, we say E2 1, 2 indicates it is happening in process 2 and 1 indicates it is the first event in 2. Similarly, E2 2. So, E2 1 happened before E2 2. Similarly, if there are two events in P1 which says E1 1 and E1 2, then we say that E1 1 happened before E1 2. Similarly, E2 2 happened before E2 3. So, these are similarly we can continue having happen before relationships. Now, using this happen before relationship, Leslie Lamport in 1970s framed a mechanism to order events. We assign timestamp to every event using this happen before relationship, ensuring causality. Almost all distributed systems use some form of logical clock. This is called logical ordering of events, and the clock that is generated using this is called the logical clock. So, here is our convention. Pi is the ith process and Eij are the ith process's jth event, and the clock we assign as a value of LC of ith process, LCI. So, we have three conditions. If in the same process Ei and Ej are two processes, Ei happened before Ej, then the time of Ei will be less than time of Ej. If P1 is sending a message M to P2, then the sending of M happened before the receive of M. Obviously, a message cannot be received before it has been sent by the sender, and the happen before relationship is transitive, which means that if Ei happened before Ej and Ej happened before Ek, then Ei happened before Ek. Unfortunately, we will see that it only causes a partial ordering. So, here is our example. If we two processes P1, P2 and these are the events and this is how the time goes. So, if we apply rule 1, we see that E2 1 happened before E2 2, 1 1 happened before E1 2, E2 2 happened before E2 3 and so on. So, in the same process, if two events have occurred, the earlier event has happened before the later event. In rule 2, we say if there is a sent message, then the message sent event happened before the message receive event. So, if M1 is a message sent, so E11 is a message sent event and E23 is a message receive event, then we have E11 happened before E23. Similarly, M2 is a message, E24 happened before E13. So, this is rule 2, and rule 3, which is the transitive rule, says that E11 happened before E24, because E11 happened before 23 and 23 happened before 24. Similarly, E21 happened before 22, E22 happened before E23, 23 happened before E24, 24 happened before E13 and 13 happened before E14. So, therefore, by rule of transitiveness, E21 happened before E14. So, what is the logical clock rule? So, the goal is to assign a timestamp to each event following causality, of course, and these are our synchronization rules. Rule 1 says a process Pk increments its clock by 1 for every event occurring in it. So, that is our first rule, by which we start with some value and we increase our clock by 1 for every event in that. And the second rule says if Pk receives a message and the message comes with a timestamp of the send event of the sending process, then Pk is supposed to update its own logical clock by this rule, maximum of its own clock and the timestamp plus 1. So, this is the second. So, we are supposed to increment our clocks according to these two rules. Let us look at this example having P1, P2 and P3. So, initially all clock values we are starting from 0. So, LC1, LC2 and LC3 are zeros. Now, we have E11 which is 0 plus 1 1, E21 0 plus 1 1, E31 again 0 plus 1 1. So, LC1 1, 2 and 3 all are 1. Now, E22 will have a value of 2, E23 will have a value of 3 and so on. Now, if LC1 having 2, this E12 is a send event and E24 is a receive event, then the LC2 value by rule 2 will change by this rule. How it will change? We have a timestamp of this send message as the send time 2 and we have to take new value of LC2 to be maximum of LC2's current value and the timestamp plus 1. So, LC2's current value is 4 and time plus 1 time send time value plus 1 is 2 plus 1 3. So, a maximum between 4 and 3 which is LC2 will be 4. So, this is how our rule 2 will be applied to all the other events. So, if we apply the rule 2, then in the second example we see that the clock value will change to LC3 to be equal to 6. And similarly, this will be actually it should have been 4, but because of this send event it has been changed to 8, right, and then it continues to 9. So, what is the causality rule? We have the Lamport's clock which follows the rule of causality. That means, if a value of a clock changes, if an event is a happened before relationship, then the timestamp of the earlier event has to be less than the timestamp of the later event. So, E11 and E12 1 less than 2. Similarly, in another example 1 2 1 3 1 less than 8 and third example 1 less than 2, fourth example again 1 less than 6 and so on if we look at this all. Now, all they are following transitivity as well. Yes, we look at the transitivity E11 by transitivity follows E33 and the clock values are 1 and 7. So, 1 is less than 7. Similarly, we have another example E21 if it happened before E14 by transitive rule and the values are 1 and 9. So, 1 is less than 9 and so on. But this is partial ordering. Why is this partial ordering? We cannot put any order between certain events like E11 and E21. Let us look at this E11 and E21. We look at the clock values, they are the same, but we cannot have any ordering. Similarly, 1 3 and 3 2 are two events where no ordering can be put and so on. So, what is the problem of Lamport's clock is that if E1 has happened before E2, then timestamp of E1 is less than timestamp of E2, but the reverse is not true. What is the reverse? If we look at the timestamps and we see the timestamp of E1 is less than the timestamp of E2, then we cannot say whether E1 happened before E2 or E1 and E2 are concurrent. So, two events for which no order can be put are called concurrent events. So, therefore, logical time can be used only for partial ordering. So, all these events where E11 has timestamp equal to E12, E13 has timestamp less than E32 and E24 has timestamp greater than E13, but these are all concurrent events. So, looking at the timestamp, it is not possible to decide the time. So, the solution lies in the vector clock. This is used in key value stores like RIAC. What is a vector clock? In a vector clock, we have n elements in comparison to one value in logical clock. Every process will maintain a vector in the form of a clock, and the in this vector the ith element the value of ith element is the clock value of the ith process. So, the jth element of the vector clock in Pi will be Pi's best guess or the highest value of Pj. I do not know exactly, but I think this is the highest value of j. So, similar to logical clock, a vector clock also will make changes in the clock values, and a message will be given again another vector of 1 to n. So, what are the rules of vector clock? The first rule say that a process Pk increments only the kth part of the vector Vck by 1 for every event occurring in the process. And the second rule says that if it is a receive message, then it checks all the values and takes the maximum between its own clock and the time, the vector time in the message. So, here is an example. So, all the values initially 3 processes. So, 3 values in the vector, all are zeros. Now, the first event 1, in an internal event it increments only its own clock. So, therefore, it will change only the first value in P1. So, it on E11 it becomes 1 0 0. Similarly, in P2 it will change only its own clock 0 1 0, and in P3 it will be 0 0 1. Now, when it is a sent message, this 0 1 0 has to be recalculated. How we recalculate this value? This message is coming with the clock value of 0 0 1, because E31 is a 0 0 1. So, therefore, this message is coming with the 0 0 1, and how we change it? This is our rule for all I, maximum of the ith value in the my vector and the ith value in the message vector. So, first one maximum of the value 0 and 0. So, therefore, the value of the first vector's place is 0. The second value is maximum of 1 and 0. So, therefore, it is 1, and the third value is between 1 and 0. So, therefore, it is 1. So, the final value of this event will be 0 1 1. Similarly, if we see that this is 2 0 0, the vector clock is 2 0 0. So, the time stamp will be 2 0 0, and this will be 0 0 2 1. So, it will be 0 2 1. When we consider this message, the timestamp of the incoming message and the original timestamp, we see that between 0 and 2, 2 is max. So, the value is 2. Between 2 and 0, 2 is maximum. So, the value is 2, and 0 and 1, 1 is maximum. So, the value is 1. So, the new value of the receive event is 2, 2, 1. Similarly, here 3 0 0, and this value is going to be 0 0 2, and when we have 0 0 2 and 3 0 0, we compile these according to the vector clock and we get the value 3 0 2. We can continue giving examples of this to indicate the vector clock. So, therefore, how does it solve our problem of concurrency? Vectors follow very specific rule. Two vectors Vt1 and Vt2 are equivalent or same if and only if for every value of I, Vt1i is equals to Vt2i. So, two vectors are having the same value if each vector value inside each vectors are identical, whereas Vt1 is less than equals to Vt2 if for all I, Vt1 is either less than or equals to Vt2. Two events are causally related if and only if Vt1 is less than Vt2. So, how do I say less than Vt2? If Vt1 is less than equals to Vt2 and there exists such j's for which Vt1 of j is less than Vt2 of j. So, therefore, all values will be less than or equal to, and some values will be at least less than, and with that we can say that two vector values VT1 and VT2 are related with the less than. Now, this is the magic of vector clock, which we missed in which we do not have in a logical clock. In a vector clock, if VT1 and VT2 follow a certain relationship, then looking at those relationship we can claim that the two events follow a certain order. The two vectors are concurrent if and only if we say that VT1 less than equals to VT2 is not true and VT2 less than equals to VT1 is also not true. So, therefore, events will be concurrent if neither VT1 is less than VT2 nor VT2 is less than VT1. If we look at this example, then we will see that this event 1 0 0 and this event 0 1 1, it is neither VT1 less than VT2, because there is this 1 and 0, there is a this is more than this. On the other hand, it is nor less than VT2 less than 0, because VT2 has one component which is greater than VT1. So, these are two events which are concurrent events. So, we see that E11 happened before E12, because 100 is less than 200. E12 happened before E22, because 200 is less than 221. We see that all vector values do follow the relation of less than. E12 happened before E22, because 100 is less than 221. Similarly, 31 happened before 22. So, looking at the clock values, we can say which event has happened before which event. Now, if we look at 1 3 and E22, then we see that 3 0 0 and 2 2 1. These two vector clocks do not follow either less than or greater than relationship. So, why they do not follow? Because E13 has 3, here it is 2. So, this is bigger. Now, this is 0, this is 2. So, this is bigger, this is 0, this is 1. So, this is bigger. For one count, E13's value is larger, for the other counts E22's value is larger. So, therefore, these timestamps do not follow any relationship, and hence these events are concurrent events. So, in this module we saw that Lamport's logical clock is good, simple, we can easily implement it, but it provides only partial ordering of events, and whereas vector clock, although it is a little more complicated in the sense that we have to do a little more complicated calculations, they are able to completely order all the events. These are our references. Thank you.